Welcome to rankstudent.com, the site preferred by millions of students around the globe for digital education in science and technology. I'm Dr. Ahmed. I'll be your host for this important chapter on rotational motion. The types of motion of a rigid body can be classified into translational motion, rolling motion, rotational motion, or motion in precession. For instance, we have here a block that is sliding down an inclined plane, and that's an example of translational motion. In the second part of the diagram, we have a ball rolling down an inclined plane. This ball is rolling around its own axis that passes through P1. That's an example of rolling motion. At the same time, a point P2 that is not at the center of the ball is rolling and at the same time rotating. And that's an example of rolling and rotational motion. In the third example, we show a top, something that we all play with. A top rotates around its own axis, which is shown here, rotation, but at the same time it wobbles around a vertical axis. So it has two types of motion, a rotational motion around its own axis, and a precession motion around a vertical axis. This type of motion is very important in the design of gyros. Now let's look at the physics of a system of particles. The center of mass of a system of particles is the mean location of a distribution of masses in space. For a one-dimensional system consisting of masses m1, m2, etc. up to mi, the location x at the center of mass is given by x equals summation or sigma mixi divided by sigma mi. You multiply the masses by their position divided by the sum of the masses, which is designated by the letter capital M, the total mass. In a three-dimensional space x, y, z, similarly, x equals sigma of mixi divided by sigma mi, and same kind of definitions along the y and the z axes. In general, if we express the above equations as a vector, r equals sigma miri divided by sigma ri, where r is the vector locating the center of mass of a cylinder of masses whose vector locations are r1, r2, ri. Now let's look at Newton's second law as applied to a system of particles. We can treat a system of masses as if all the mass of the system is concentrated at the center of mass Cm, and all the external forces are applied at the center of mass, namely ma equals F external, where m is the total mass of the system, a is the acceleration of the center of mass, and F is a vector sum of all the forces acting on the center of mass. The internal forces balance out with each other in accordance with Newton's third law of motion and are not considered in this equation. The definition of the total momentum of a system of particles. The total momentum P of a system of particles is the product of the total mass of the system m and the velocity v of its center of mass Cm. P equals mv. It follows that the external force F external equals m dv by dt, which is equal to ma. P, F external, v, and a are vectors. We must remember these. P equals mv. motion of a specific particle in a system of particles. So you have a system of particles, you're looking at the specific motion of a specific particle. The motion of a specific particle in a system of particles can be considered as the sum of the motion of the center of mass and the motion of that particle with respect to the center of mass. For example, a man who is seated at the back of an airplane experiences greater vibrations than a man seated near the center, because the motion of a point at the back of the plane is the sum of the motion of the center plus the motion of a point in the back of the plane with respect to the center. That's why we try to get a seat in the front of the plane or the center of the plane rather than the back of the plane. And the same thing is true of other vehicles too. Vector products. Again, definitions. The vector product, also called the cross product A cross B, of two vectors A and B with included angle theta is a vector C whose magnitude is AB sine theta and whose direction is a vector perpendicular to the plane of A and B. The direction is given by the right-hand rule. This is illustrated in the diagram on the right-hand side, where we have the vectors A, B, and we have the cross product of A and B along the vertical axis C. What are the rules of cross products? A cross B is not equal to B cross A. Indeed, A cross B is equal to minus B cross A. Associative rule. A cross B plus C is equal to A cross B plus A cross C. The cross product of a vector A with itself is 0. The cross product of a unit vector I and a perpendicular vector J is equal to a vector which is perpendicular to both I and J. In this case, I cross J equals K. Similar definitions apply to J cross K and K cross I. Now let's look at A cross B, defined in terms of the components AX, AY, AZ, and BX, BY, BZ. The result is indicated in the expression here, and the resultant vector can be written as a two-dimensional matrix, which is done in the diagram on the right-hand side, where we have shown the cross products of A and B, the dot product, as well as the cross product, two-dimensional matrix. Now, the algebra of matrix must be familiar to you. If not, get familiar with them as to how to multiply them. In this example here, for instance, A cross B. The way you multiply two vectors A cross B is the following. It's very simple. You write down I, J, and K, I, J, and K. The components of the vector A and B, 3, minus 4, and 5, minus 2, 1, and 3. Then A cross B is the following. I, you cross out the column and the row, and then you multiply it, the next component minus 4 with the cross component of the other vector, minus 4 times minus 3, minus 5 times 1. Similarly, when you wish to calculate the component along the j-axis, you cross out the column and the row containing j. You start with 5 times minus 2, minus 3 times minus 3, plus k times, cross out the row and the column. Then you start with 3 times 1 minus 4 times minus 2. These should be mastered. You should know how to multiply the components of a matrix and calculate the resultant vector of a cross product of two vectors A and B. Here what we have done is to summarize the correspondence between linear and rotational motion. Linear motion terminology is by now familiar to you. Displacement x, velocity v, acceleration a, force F, mass m, work F dx, etc. The corresponding terminology for angular motion is given in this column here. Corresponding to displacement, we have the angle. The velocity is measured in angular velocity, omega. Angular acceleration is the rate of change of angular velocity, d omega by dt. The torque is I times alpha, where I is the moment of inertia, which corresponds to the mass m in a linear motion. The work W is tau d theta. Kinetic energy is I omega squared over 2. Power P equals tau omega. And angular momentum L equals I omega. Tau here is the torque. You should be familiar with this terminology, master it. And the mastery of the terminology will enable you to tackle specific problems in angular motion, just as the mastery of the terminology in linear motion will help you tackle specific problems in linear motion. Now, a few more definitions. The angular velocity omega is defined in terms of the linear velocity v by the relationship v equals r omega. Omega is a vector. By the right-hand rule, it is perpendicular to the plane defined by r and v. Similarly, the angular acceleration alpha is the rate of change of the angular velocity. Alpha equals d omega by dt. These definitions are illustrated in the diagram on the right-hand side, where we have a point P which is rotating in an axis going through the center C. The rotation, the angular velocity, is designated by omega. The point P encounters the angular velocity omega as well as a linear velocity v, which is tangential to its path of rotation at the point P, illustrated by the vector v as in here. Torque is the moment of force. It is defined by the cross product tau equals r cross F. Torque is a vector perpendicular to the direction r and the force F. Its magnitude is given by Rf sine theta, where theta is the subtended angle between r and F. In the diagram on the right-hand side, we have a point P, and the force acting on the point P, the location of point PR, so that tau, which is r cross P, is a vector perpendicular to a plane defined by F and R and indicated by the axis along which the tau is acting, shown in here. This is r sine theta, the projection of r on the xy plane, the force F, and tau, which is perpendicular to RF. The angular momentum L is the moment of linear momentum P. It is defined by the cross product L equals R cross P. Angular momentum is a vector perpendicular to the direction R and linear momentum P. Its magnitude is given by Rp sine theta, where theta is the subtended angle between R and P. Torque is defined as the rate of change of angular momentum, as seen by dl by dt, the rate of change of angular momentum, which is equal to r cross dp by dt, which gives us r cross f, which is the torque tau. Now the angular momentum of a system of particles. The rate of change of angular momentum of a system of particles about a point is equal to the sum of the external torques acting about the same point. dl by dt equals tau external. If the total external torque is 0, the angular momentum L is conserved. This is the rotational analog of the conservation of linear momentum. Now, the study of equilibrium. For a rigid body to be in equilibrium, the sum of the total forces and the sum of the total torques acting upon the rigid body must be 0. F1 through Fn equals 0. Similarly, the sum of tau 1 through tau n should be equal to 0. These are both vector equations. Therefore, the sum of the components of the total force and the total torque must be 0 along each of the 3 axes. Two equal and opposite forces F separated by a distance d are called a couple. They exert a torque on the body tau equals to Fd. That is the definition of couple in physics. Applying these equations to a lever, for instance, we have a yo-yo, and we're all familiar with them as children sit on them, one on either side, not at equal distances from the point of support. One is at a distance d1 from the support, and the other one is at a distance d2 from the support. By equilibrium, R equals F1 by F2. R equals F1 plus F2. And taking moments, d1 F1 equals d2 F2. The distance d2 and the distance d1 are related through mechanical advantage. Mechanical advantage is defined as F1 by F2 equals d2 by d1. No wonder Archimedes, the great Greek physicist, said it one time, reportedly, "Give me a lever and I'll move the earth." Makes sense theoretically, at least. Center of gravity. The center of gravity is the point about which the total gravitational torque is 0. The center of gravity and the center of mass coincide for a co-extended body, where g, the acceleration due to gravity, does not vary from point to point. This is true of most rigid bodies that we touch in the physical world. The center of gravity is usually located by hanging the body by a string at various points, and these directions in which the body is hung intersect at the center of gravity, as illustrated in the diagram on the right-hand side. A definition of moment of inertia. The moment of inertia of a system of particles about an axis of rotation is defined as I equals miri squared, where I varies from 1 to I. The kinetic energy of the body is defined as Ke equals half of I omega squared. The radius of gyration K of a body is defined as I equals mk squared. We must be familiar with these definitions. Now the theorem of perpendicular axis. The moment of inertia about an axis of rotation perpendicular to the xy plane, that is the z-axis, is equal to the sum of the moments of inertia about the x and y axis. I sub z equals I sub x plus I sub y. the moment of inertia about the z-axis is equal to the sum of the moment of inertia about the x-axis and the y-axis. Similarly, the theorem of parallel axes. Here we have shown two parallel axes, z and z prime. The moment of inertia about an axis is equal to the moment of inertia about a parallel axis through the center of mass plus the mass of the body multiplied by the square of the distance between the two axes. So again, in this diagram here, I sub z prime is the sum of I sub z plus the mass m located at O times the square of the distance between the two axes, which is A in the diagram. Similar to kinematic equations for translational motion, we have kinematic equations for rotational motion. Omega equals omega 0 plus alpha t. Theta equals theta 0 plus omega 0 t plus half of alpha t squared. Omega squared equals omega 0 squared plus 2 alpha theta minus theta 0. These equations for rotational motion correspond to the kinematic equations for linear motion. The instantaneous power P in rotational motion is given by P equals the torque tau times the angular velocity omega, which corresponds to P equals Fv, power equals force times velocity for a linear motion. Now, the very important law of conservation of angular momentum. If the total external torque on a body is 0, the angular momentum L is conserved. L equals I omega equals constant. This is the rotational analog of the conservation of linear momentum. Let's consider rolling motion. In a rolling motion, the velocity of any point on the rim is the sum of the velocity of the center and the velocity of that point with respect to the center. In the diagram on the right hand side, the velocity of point P2 is the sum of the velocity of the center C plus the velocity of point P2 with respect to the center C. The kinetic energy of a body in rolling motion. A rolling body has two components to its kinetic energy. First, a linear component due to the motion of the center of mass Cm. Then there is a rotational component due to the rotation of the body, which is the kinetic energy becomes the sum of the rotational energy, half of I omega squared, plus the component of the linear motion, half of m vcm squared, where vcm equals r omega and I equals mk squared. K is the radius of gyration. Let's go over it again. The kinetic energy of a body in rolling motion, it has two components, a linear component and a rotational component. So the kinetic energy is half of I omega squared plus half of m vcm squared, with vcm, velocity of v of the point C with respect to a point m. vcm equals r omega and I equals mk squared. K is the radius of gyration. To summarize the correspondence between linear and rotational motion once again, we must be familiar with the terminology for the linear motion and the terminology for the angular motion. I would recommend that you log on to www.rankstudent.com, download onto your mobile phone, and practice with actual examples from previous tests. Rankstudent.com has provided you almost 100,000 questions, answers, and answer elaborations from board, JEE, NEET, and JEE Advanced exams. What we have done is to review the basic concepts in rotational motion, familiarize ourselves with the vocabulary used in rotational motion, and highlight the equations that are used in analyzing physical problems in rotational motion. The more practical problems we solve, the better we understand the physics of rotational motion. This is in general true. We must listen to the lectures, study the textbook, and then practice with a large number of actual examples. It is only practice that will solidify an understanding of the concepts that will help us see the patterns in the physical universe, so that when we encounter a new problem, we're able to use those patterns to analyze and solve that specific problem. I thank you for your attention.